Hello students, in previous class I have discussed about the concept of magnetic field and we have learned that a current carrying conductor creates magnetic field around it. That means this is a current carrying conductor. This current carrying conductor creates magnetic field around it. I have already learned this concept. Now we do not know the value of magnetic field in this point, in this region. So we have to calculate the value of magnetic field in this region. So if I want to calculate the magnetic field at the region due to this current carrying conductor, you have to know a law. This law is called Biot-savart law. So we have to learn about Biot-savart law. Biot-savart law. So Biot-savart law is used to determine the magnetic field due to this current carrying conductor. So suppose this is a current carrying conductor. This current carrying conductor, here is current is I, and if I take a very small infinitesimal length dl, and if I want to calculate the magnetic field at P, and this distance is R, then we have to calculate the magnetic field at point P. What will be the value of magnetic field at point P? Here you see the variable physical quantity. Number 1, the variable physical quantity is this current. That means here is variable quantity is current. So this magnetic field here, suppose this magnetic field is dV due to this small element dl. So if I increase the current, then the magnetic field will be increased. So if I decrease the current, then the magnetic field will be decreases. So the magnetic field at the point P is directly proportional to this current. So second variable physical quantities is dl. If I take greater length of this current carrying conductor, then the magnetic field at the point will be increased. If I take small value of dl, then the magnetic field due to this dl will be decreased. That means this magnetic field is proportional to this elementary length. Now the third variable physical quantity is distance. That means distance between dl and P point. So if I suppose this is a magnetic field B1, here is magnetic field is B2, here is magnetic field is B3. So for this current carrying conductor, the magnetic field at point in this point, and here is at this point, here is at this point. So if I increase the distance, then the magnetic field will be decreases. So here B1 greater than B2 greater than B3. So if I increase the distance from this current carrying conductor, then the magnetic field will be decreases, and it follows the inverse square law. That means dV is proportional to 1 by r square. Number 4. What is the number 4? Suppose if I want to calculate the magnetic field at point A for the same elementary length and the distance is r. Distance is r. Is here. Suppose this is magnetic field B1 due to this elementary length. If I take the same length r and here is magnetic field B2. If I take the same length r at this is magnetic field B3 and the same length r, the magnetic field is B4. So at this point magnetic field is maximum. If I take this point, so here in this case B1 less than B2 less than B3 less than B4, because we have learned that the magnetic field due to this current carrying conductor is making in this way. So the magnetic field in this region will be maximum. If we go along this direction in the same distance, then the magnetic field will be decreases. Suppose this is angle theta 1 and this is angle theta 2. This is angle theta 3 and this is angle theta 4. So here when theta is increase, magnetic field will increase. Theta is increase, then magnetic field is increase. And we know if I take the sine value, suppose 0 degree, here is 30 degree, here is 45 degree, here is 60 degree, here is 90 degree. Now if I take the value of sine theta, then here will be 0, here will be 1 by 2, here will be 1 by root 2, here will be 1 by root 3 by 2, here will be 1. So here the sine theta value will be increases. So for this case, so it is depend of the angle between DL and R vector. So this can be written as dV samanupati. dV is proportional to sine theta. dV is proportional to sine theta. So when theta is increased, the magnetic field is increased. So is proportional. So if theta is increased, only sine theta. If theta is increased, the sine theta value of sine theta will be increased. That's why we take the sine theta. So here if I combine this equation, so we can take the value. If I combine this equation, then it will be dV is proportional to I dl sine theta divided by r square. Then it will be dV equals to k I dl sine theta divided by r square. This is a proportional constant. This constant is depend on the unit system of unit, that means unit, and is medium. So if I take CGS unit and SI unit system, in CGS unit K is 1, so dV will be I dl sine theta divided by r square. And if I take SI unit, then K will be mu 0 divided by 4 pi. Mu 0 is the permeability of vacuum, and it can be written as dV equals to mu 0 by 4 pi into I dl sine theta divided by r square. And the unit of this case equals to Gauss, and it will be Tesla. So this is the 2 unit system of this Biot-savart law. The 2 equation in SI CGS for unit system and SI unit system. Now you have to know the limitation of this Biot-savart law and applicable of this Biot-savart law. Here, number 1, where this law is applicable, where this applicable, where this law is applicable, you have to mind it that this elementary length, the magnetic field is P. So this Biot-savart law is applicable for infinitesimal small segment of length. So this law is valid for very small element of this current carrying conductor. So if you want to calculate the whole for the magnetic field due to whole current carrying conductor, you cannot apply directly the Biot-savart law. You can use the elementary length. For elementary length, the magnetic field at this point, then you can use the integration. So you have to mind it that Biot-savart law is applicable for this elementary length. Its elementary length also is called current element. IDL is called current element. So you current element. So you may say that Biot-savart law is applicable for current element. Okay, so you have to mind it. Number 2, limitation of Biot-savart law. What is the limitation? Limitation is number 1, when is most perfect in vacuum. But if you apply on a ferromagnetic material, if you want to calculate the magnetic field inside the ferromagnetic material, then the theoretical value and experimentally value is equals to some differ. So Biot-savart law is applicable or most perfect in vacuum. When it is used on a ferromagnetic material, then the calculated value and the theoretical value does not match, slightly differ. So you may say that what is the limitation of Biot-savart law? The limitation is it is most perfect in vacuum, but in ferromagnetic materials the calculated value and the theoretical value is somehow small differ from each other. Okay, this is the limitation of Biot-savart law. Now you have to know the various form of Biot-savart law. So next is various form of Biot-savart law. So number one is the vector form. Number 2 is in terms of current density. Now you have to find in terms of charge and velocity. Here we have deduct that dV equals to mu 0 by 4 pi I dl sin theta divided by r square. Okay, this is the current carrying conductor. This is the dl, direction of dl is along this direction, and this is the direction of r. An angle between the dl and r is theta. So if I take the dl cross r unit cap, that means the unit vector along the direction of r, then it will be dl, magnitude of dl, then magnitude of unit vector, then sine theta. Here the dl, the angle between dl and r unit cap is theta, so this will be the value of the unit vector is 1, so it will be dl sine theta. So we can replace dl sine theta by dl cross r unit vector. So the magnetic field at this point P, it can be written as vector form is mu 0 by 4 pi I dl cross r unit vector divided by r square. So it can be expressed in this way, also in this way, I dl cross, here is r vector, then it will be r cube, because r unit vector equals to r vector divided by r vector, magnitude of this r vector. So this is the vector form of Biot-savart law. If I want to express this expression in terms of current density, what is the current density? Current density is defined as current per unit area. So if I multiply in both, suppose this is the current carrying wire, this area is A. If I take small distance dl, the volume of this volume will be dV equals to A into dl. We multiply in both I and A by dl. So it can be written as IDL, here can be written as dV, because IDL is dV. So IDL equals to J dV. So here you see, you have to replace the IDL by J dV. So dB equals to mu 0 by 4 pi, here is this IDL is replaced by J dV, that means J vector cross r unit vector divided by r square into dV. It can be expressed also in this way, J vector r vector divided by r cube into dV. So in this way you can express the formula magnetic field by current density, okay, in the form of current density. Now if you want to express the equation magnetic field in terms of charge and current and velocity, then it will be, here is IDL, here is IDL. I can be written as Q by dt, and here is dl. So it will be Q into dl by dt. So it will be, can be written as Q into V. So you have to replace IDL by QV. So dB vectors will be mu 0 by 4 pi q v cross r unit vector by r square. It can be written as 4 pi q v cross r vector divided by r cube. So this is the form of Biot-savart law. Here we have discussed that what is the form of Biot-savart law, and here we have discussed that the magnitude of this magnetic field created by a current carrying conductor. So magnetic field is a vector quantity. So you have to calculate magnitude and also the direction. So here we have calculated the magnitude already, but how to calculate the direction, how to define the direction of magnetic field? There are 3 or 4 laws for determining the direction of magnetic field, but I recommend to use the laws of vector product. Okay, how to calculate the direction of magnetic field? Suppose this is a current carrying conductor. This current carrying conductor here is R, this point P. You have to find out the magnetic field at this point and the direction of this magnetic field for this current carrying conductor. So we have learned the vector form of magnetic field. So mu 0 divided by 4 pi I dl cross r vector divided by r cube. This is the vector form of magnetic field due to this current carrying conductor. If this is a vector and this is a b vector, if I calculate the cross product a cross b, the direction of the a cross b will along this direction. Okay, suppose this is a dl, and this is a r vector. The direction will be dl cross r vector along this direction. So use this vectors laws. Okay, vector concept of vector. Using this vectors concept, you can easily find out the direction of this magnetic field. So direction of dl along the direction of current, always the direction of current. So this is my right hand. I spread my forefinger along the direction of current and I turn around this forefinger towards the direction of R. So in this case, the direction of magnetic field is into the board. So the magnetic field here will be inward of this board. If I want to find the magnetic field at this point, then what will be the direction? Here is the magnetic direction of R is along this direction, and suppose this is my right hand. I spread along the direction of dl, that means current. I turn this forefinger toward the direction of r vector, then the direction of magnetic field along this direction. So this is the direction of magnetic field is along this direction. This is inward and it is outward. Okay, this is the magnetic field. Outward can be represented by a circle and a dot, and inward is represented by a circle and cross. Okay, this is the direction, how to calculate, how to determine the direction of a magnetic field. Okay, I recommend